So we continue with the ODE solvers. It's a huge topic. Okay, so let's start this. So ODE solvers is very important for science and engineering. No? When we have nature is basically, well, in modern description is that we describe using differential equations. Okay, so time is continuous, so it becomes differential equation, Newton's law, Schrodinger equation, which are the key for describing all sorts of phenomena. And so ODE solvers are really important. Okay, so I did cover last time Euler forward scheme. I introduced how to solve it. So we discretize it in time, and then we time advance the variable. So you imagine that we have equation. So the equations which we solve are Newton's law, Schrodinger equation, but we'll do ODEs. So Newton's laws, but Newton's laws is second order, so we can convert second order to first order, which I described in the last class. Any nth order equation, we can make it in first order xt. Okay, it could be coupled, but we'll just focus on solving single first order equation. Then we'll combine. I mean, we'll try to solve a set of ODEs, but that will follow maybe not today, but on Thursday. Definitely not today. Okay. Now we solved using Euler forward scheme. So this was discretized. The time was discretized. So we started with t0, So we have tn, and we go to tn plus 1. Okay. So that's, so we want to go from here to there. So Euler forward, okay, forward, which I did in the last class, which is xn plus 1 is equal to xn plus delta t times f. Now, where do you compute f? F we computed xn and tn. So these are, I mean, we are going from tn to tn plus 1. So I know my values of x as well as time here. Okay. So this is called explicit scheme because we can compute this f easily. Okay. So this is explicit scheme, which I did in the last class. Okay. Now, there are problems with explicit schemes. What is the problem? It is unstable. So we had, well, it's conditionally unstable. So we need to choose delta t. So we remember we had equation x dot equal to alpha x. Alpha negative, my real solution is supposed to be decreasing in time, but it turns out if alpha delta t is greater than 2 by alpha, then my real solution, well, numerical solution oscillates and grows and oscillates. So that's why it is stability is a problem for Euler forward. So implicit schemes are better for stability, and that's what I will show today. Okay, so implicit scheme, what do we do? So we go from again tn to tn plus 1. You go like that, but you compute f not at here, not here, but at the forward time here, okay, which is xn plus 1 and tn plus 1. Okay, so we have to compute f, but okay, I mean it's an integral, so we can choose different schemes, and this one scheme. So it is Euler implicit scheme. Now, this looks nice, but it has a problem. No? Why? What is the problem? The problem is that I don't know xn plus 1. It is still not computed, right? I mean, xn plus 1 is, I want to get xn plus 1, but I'm supposed to compute f at xn plus 1. Now, so that's a problem. And that is why it is called implicit scheme, because my answer, which is here, depends on answer itself. So f computation can be quite complicated. I'm just going to show you one example. Okay, so let's try to do it for simple thing like x dot is alpha x. Okay, now For this case, it is easy. So I'm going to solve this equation, which is trivial, but it is very useful for stability analysis, accuracy estimates, and so on. So if I just put xn is we have xn plus delta t. Now f, this f, right? So f is alpha xn plus 1. Okay. Now it's a linear equation, and in fact we can just take this to the left hand side, and you get 1 minus alpha delta t is xn plus 1. Right? So xn plus 1 equal to 1 divided by 1 minus alpha delta t xn. Okay. So it is easily solvable, no problem. Okay. Now I will come back to this expression in a minute. Okay. So, well, let me just state it right now. We will repeat it afterwards in a quick way. So this has advantage. Why? Imagine alpha is negative, real and negative. And this solution will decrease with time. What happens to this solution? Will it decrease in time? Yes, it will decrease in time because this minus alpha is positive. So whole thing, this denominator is greater than 1. Okay. So the prefactor here, prefactor is less than 1. Whole prefactor, this is together. Okay. So it is positive and less than 1. So xn plus 1 modulus. Xn plus 1 could be negative as well. Huh? So, but modulus of this will be less than xn when alpha is negative for this case. So that means x is decreasing in time, which is what we want. Real solution is decreasing in time. So implicit scheme, this is the advantage of implicit schemes, that it is unconditionally stable, right? Because stable for all delta t. You can choose a large delta t, no problem. It will be stable. It will decrease. Large delta t is not accurate, but it's stable. Okay, or the real computations of numerical solution will decrease in time. It will decrease more rapidly than what the real solution says, but because error, but it will decrease in time. Okay, so this is advantage. So this is unconditionally stable. Okay. Now we can also very easily show that if alpha is complex but real alpha is negative, then also I expect the solution to decrease, and it happens here as well. Okay, so that I will leave it for you to do an exercise. Okay, now what is the difficulty with this scheme? So not everything is rosy. So suppose we have a equation of this sort. Okay, now this is f of xt. Now what happens with Euler implicit scheme? So xn plus 1 equal to xn plus delta t, okay, times this. But this is computed at later time. So tn plus 1, okay. So tn plus 1 is t plus delta t, right? Exponential minus xn plus 1. So now we got this equation. Now this is a problematic equation, no? It is not like x dot equal to alpha x. Solving this equation is in fact is a nightmare, right? Well, not so much a nightmare. There are schemes to solve this. So my unknown is appearing in the right hand side with the exponential form. So this is a nonlinear equation. Okay. It's a nonlinear equation, and there are ways to solve it. Okay, we'll come to it later, but it's not easily solvable. You need a kind of specialized algorithms for this. Okay, so that's the difficulty. Nonlinear equations, you need to solve nonlinear equations if you are right hand side is nonlinear. Let's do another example. Okay, so this is the equation which I wrote. So this equation is also nonlinear, x squared minus 100x. So we have to put right hand side like that. Now this equation has a solution, but it's a quadratic equation, right? It's xn plus 1 squared. So it has two solutions. Now, which one should I choose? I mean, I can't put two solutions, right? I mean, that will be or can't do a random coin toss. You have to choose the appropriate solution. So we know that for well, you need to make a guess. Not you need to make some kind of actually not a really guess. It's a back and forth problem. So you can solve this with Euler forward, maybe Euler forward, and see what is the how the solution looks like. It require don't solve it precisely, but just make an approximate solution, and you find that this solution does decrease in time. Okay, because this minus 100x. X squared will try to grow it, but x is small. Minus 100x is really a dampener. It dampens the solution very fast, and so this is damping solution. So we want my real solution, when computation solution or numerical solution, also to decrease in time, and it turns out you should choose this solution, which is given below. The other solution, quadratic solution, is in fact increasing in time. Okay, so that's what we need to do. Okay, and there's a small code for this, and this is basically very similar to Euler explicit. So we find number of steps given t final and t initial and then dt, and I just do a loop. Okay, so xn plus 1. This is that formula which I have in the right, which in the earlier slide. Okay, it's just straightforward, but you need to basically solve the nonlinear equation. Sometimes it's easy, like for quadratic is easy, but for exponential it is not easy. Okay, now this is a solution. So numerical solution is this one, and this is the exact solution. Okay, and by the way, please don't get misled by these kings. I choose a finite delta t. That's why the kings are there. I really is 0.01 is my dt. Okay, so because I had to choose finite delta t, and I chose pretty large delta t, 0.01. I could have choose 0.001, then it will look somewhat smooth and it will be more accurate. But okay, so so error is this. Now, what is accuracy of Euler backward or Euler implicit? So we can expand. Well, basically, the exact solution is not that. So I just expand f here, which is x dot at n plus 1, which is, I mean, when we do Taylor expansion, so which is x dot at n. N means Tn. Okay, then delta t x double dot, then half delta t squared x triple dot, and so on. Now, what is exact xn plus 1? Which is xn plus delta t x dot plus delta t squared by 2 factorial to x double dot, and so on, right? Now compare. So what does Euler give us? For Euler, so this is exact. Okay. Of course, I have to keep all the terms. I use the notation HOT, hot, means higher order terms. Numerical will be xn plus 1, xn plus delta t, and just substitute these things here, f, right? So x dot plus delta t times delta t here, so delta t squared x double dot, and so on. Okay. Next is next is this term, but you can immediately see there is a problem, right? Between these two, exact and numerical. There's a difference is where difference is right here. So my numerical solution is delta t squared and my exact solution delta t squared by factorial 2, or which is 2. So my error epsilon n, which is exact minus numerical, that is what my definition is. Some people use other way around, but I use exact minus numerical, which will be minus delta t squared, right? This one minus this by 2x double dot. So my error is order delta t, well, plus higher order terms, but that's for small n of delta t, this term will be dominant. Next term is delta t cube. So imagine that I use 10 power minus 2, then this is 10 power minus 4, and next is 10 power minus 6. So we can ignore 10 power minus 6 for estimates. So my error is of the order of delta t squared. So we write that order delta t squared error. And this scheme is first order accurate. Accurate only up to delta t. Accurate part is only here. This is the accurate. First order accurate. Okay. These are words you should remember. Okay. Now people will ask you, how accurate is your scheme? So you say, well, it's first order, second order, third order. So we do that. We did this before. I mean, we've been doing it for interpolation, for differentiation, and so on. So for OD solver also we can estimate like that. Okay. Stability issues. I already done that sometime. I mean, some time back. So here it is unconditionally stable. For any delta t stable, which is a very good thing. Okay, so we want our solution to be stable. But stable doesn't mean that you can use a large delta t, very large delta t. Your solution will be inaccurate. So we please keep in mind that I want accurate and stable. We want both. It was pretty short thing, but important. Please remember that implicit schemes are typically stable. That gives you more stability. But the problem is that you need to solve nonlinear equations if your f is nonlinear.